Example 1.3.3, using the data from figure 1, estimate the overall efficiency of the electric energy system. So I've gone ahead and copied and pasted figure 1 into the problem statement. If you can't read this, go ahead and just look it up in the textbook. It's in the you can see the figure yourself. So anyway, we need to look at this figure and extract the information from it. What is it that we're going after? Well, we're calculating efficiency, eta, Greek letter eta, and that's output over input of a system. So in this case, we're looking for energy, usable energy output divided by usable energy input. So E out over E in for this. So we need to get those two numbers from figure 1. And so I'll start with the easy one, the input energy to the system. And so we need to look at the diagram and figure out where that energy input is coming from. And so inputs on flow diagrams come on the left hand side. A lot of times we call those the tails, and so we need to look at the tails for these givens. So I'll start to write those here. So divide the diagram in half. Roughly the left side, the tails represent the inputs, the right side represents where they go to. So it gives you a lot of information, but the one we're looking for, the usable one here, is the total energy to generate electricity. We see that's 40.04 quad. So I know that can be a little tough to read there, but E input is 40.04 quad. That number just sums all those tails that are to the left of it. So it sums coal, nat gas, etc. So now we need the outputs, which as I said earlier, are the arrowheads. This one doesn't have a nice little summary for us to use it, but broadly what's happening is of the energy generated, a lot of it's just lost in waste heat. That's that big arrow at the top. And then we get what we call gross energy generation. That's the actual electricity coming out of the generators themselves. And so you can see that that number is does not include the plant usage, and so there's some loss there. So we don't want to use that number because it doesn't include plant usage. We would just have to subtract that off. And then there's the T&D losses, which we need to account for. So instead of using the gross electricity generation, what we want to look at is the net number. That number just is got gross minus the internal usage. So that 14.01 is just how much electricity is actually coming out of the power plants total. And so if we want to know how much is actually reaching the customers, we would take the net generation and just subtract off T&D losses. So that's a little calculation we have to do. So the energy output to the customers is just going to be 14.01. That already includes internal losses to the plant and usage to the plant. And then we subtract off that 1.04 quad of T&D losses. And so that's going to give us 12.97 quad of electric energy output to the customer. There's another way we could have handled that. You can see that there is a little circle here called end use. It's 13.16 quad, but the problem is that also includes some energy inputs that just didn't come from the United States, so imports, for example, and so we need to subtract off those numbers. And so if you started with the end use, you'd have you'd be including some numbers in your calculation that weren't actually part of that 40.04. So we got 13.16 quad. We need to get rid of the unaccounted fors and the imports. We do that, we get 12.98. It's pretty similar to 12.97 quad. The difference just being when you're dealing with rounded numbers to, a hundredth of a quad, these are huge amounts of energy, and so the discrepancy is really just due to rounding differences there. So now we've extracted our givens. That's pretty much the hardest part of this problem. Solving the energy efficiency formula is pretty easy. Eta is just going to be that 12.97 quad divided by 40.04 quad. Usually what we do is we represent efficiencies not as decimals. We represent them as fractions. We like to say something's 75% efficient, for example. So in this case, we get 32.4. So the overall efficiency of the U.S. electric system, from energy input to the generators to energy actually delivered to us and businesses at home, is only 32.4%. So might be a surprising finding for you, but that's the actual efficiency of the system.